Okay, so today we're going to do the last thing about uniform convergence. So, we're basically talking about how, what's good about uniform convergence, and we've seen that. I think we saw that if you've got continuous functions and they uniformly converge, then they converge to a continuous function, right? We've seen that if you've got integrable functions and they uniformly converge, they converge to an integrable function. And today we're going to talk about uniform convergence and differentiation. Okay, and so it's not true that, and Rudin gives an example, it's not true that if you have differentiable functions and they uniformly converge, that the thing that they converge to is differentiable. So that's not true. But if you put some additional conditions on, then you can get something like that. So here's the theorem. Okay. So you have a bunch of differentiable functions. And one, you require that the derivatives uniformly converge. You require that the derivatives uniformly converge, and that that the functions themselves converge at a point at a single point. Okay. So uniform convergence of the derivatives and convergence of the functions at a single point. Okay. So if that happens, then one, the functions themselves will converge uniformly. And two, the derivatives, the derivative of the limit will be the limit of the derivatives. For all x in the interval. Okay, so they'll converge uniformly to a differentiable function, which we'll call f, and f's derivative is what you hoped it would be, right? F's derivative is the limit of the derivatives of the f sub n. Okay, so this is somewhat stronger than what you would hope for, but what you hope for isn't true anyway. Okay. Everybody got the setting here, right? Differentiable functions, their derivatives converge, and the functions themselves converge at a point. Okay. So the proof of one, right? We want to see that the f sub n converge uniformly. Okay. F sub n converge uniformly. Okay. So here's the idea, right? So whenever you see these theorems, you want to think, what's really going on here? So let's think, if the f sub n converge uniformly, right? That means that all those derivatives are getting close to some function, right? Okay. So let's pretend. Suppose you knew that the f sub n's actually became a particular function. Okay, suppose that after some point in time, the f sub n primes turned into some function. Okay, right? So that they are all equal after a certain point in time, right? if all the derivatives are equal after a certain point in time, what can you say about the sequence? Right? So think like, what if all the f sub n primes actually equaled some function g? Okay. Well, what would you be able to say about the functions? If their derivatives are all equal, then what can you say about them? Yeah?
They're all the same except for the plus c.
Yes, exactly. Then they'd basically be the same function modulo some constant, right? So they would all these guys would be the same function, just at different heights, right? Okay, okay. But then we've got the second condition that that at one point the values converge. Okay, suppose you also had that, right? That there was this one point, x naught, and at that one point, all the values became, again, let's think in this sort of like morally speaking way. Suppose the values were equal at that one point. Well, then they'd be the same function, right? Because then the difference would be plus, the c would be 0, right? It would be plus 0, right? And so that's basically what's going on, right? We're gonna use the fact that the derivatives, become really close to each other, and the fact that at this one point the values become close to say that the functions themselves must converge uniformly. Okay. 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 So that's the idea. Okay. So just erase this. Okay, so okay, right. So here's the idea, right? So you say, okay, well, we want to show that these guys converge uniformly. That is by Cauchy criterion. We want to show that. We want to show that given any epsilon, there exists an n such that if n and m exceed capital N, then f sub n x minus f sub m x is smaller than epsilon, right? For all x in your interval. Right. So here's your, right, you've got these guys, right? And you want to show that, that these guys get close to each other, right? That the functions get close to each other in this relative to the sup norm metric. Okay. So okay. So okay. So so what we're going to do is we're going to bring in that extra point. Okay. So we have this point where things where the functions get close to each other. So okay, well, by triangle inequality. So by the triangle inequality, we're going to rewrite this thing as follows. We'll say, well, this thing is the same thing as fnx minus fmx. We're going to subtract off. We're going to subtract off this thing at x naught, and we're going to add it back in. Okay, and of course, we're going to break that into pieces, right? We have this thing plus this thing. Right, so fnx minus fmx minus fnx naught minus fmx naught. What's that? Okay. Okay. So can anybody see can anybody see what we can do at this point? Right, we've got only two facts. One is that these guys converge uniformly, right? What does that mean, right? These guys converge uniformly. So if we're thinking of it in terms of the Cauchy criterion, we know that given any epsilon, there's this an n past which fn prime x minus fn m prime x is smaller than epsilon. Right. So we can make the difference in the derivatives. The difference of the derivatives we can make as small as possible. Right. And we also know that these guys converge at some x naught. Right. So. I'll let you try and think about it for 1 minute and see if you can see how. So these two things will give us exactly control over it. We've broken this into two parts specifically so that we can use these two facts. Okay. So think about it for a minute. I'll walk around outside and maybe talk to each other and see if you can figure out how to use it. Okay, anybody come up with anything? Anne, yeah.
Can we rearrange the terms in the first within the first absolute value sign so that we have fn of x minus fn x naught, and likewise for the second term?
You can. You can. Why do you want to do that?
Because that resembles like the derivative at x naught. There's a limit. I don't know.
Okay. You can. I think it'll be probably easier to keep it this way because convergence means that the difference, we can make the difference small, right? So that is what we have here is rather that the derivative of the difference, derivative of the difference can be made small, right? So I think it's probably better to keep it that way, because this already as it is, it looks like the derivative of the difference, right? So let's just keep it that way. But what you're noticing is right, that there's a derivative here, right? You say, well, look, this thing is the derivative, right? So this thing is controlled by controlled by the size of the derivative, fn minus fm, controlled by the size of the derivative times the distance between them, right? So right, like the difference in the values, right? The difference in the values, right? So like, if we have, let me call the difference fn minus fm, okay? And what we have here is dx minus dx naught, right? The size of that is going to be controlled by the maximum value of the derivative times the difference between them, right? Right, like the maximum, the change is controlled by the change in time times the maximum velocity, right? That's all we're saying here, right? So, right. So what do we want to do? We'll choose. So what we'll do is the following. We'll say, well, look. Right. Choose n such that this thing, so choose n past which this thing is smaller than epsilon over b minus a. Okay, for all x in AB. Right. And then what happens? Well, this thing is going to be controlled by the size of the derivative times the change in distance, which is smaller than b minus a. So we'll get this thing smaller than epsilon. Actually, let's divide it by 2. Okay. Right. So we get, so this first part we get is smaller than epsilon over 2 b minus a times the distance between x minus x naught. But that's smaller than b minus a, right? Which is smaller than b minus a. And so we end up with, let me just replace that with b minus a, and we get epsilon over 2 for that first part. Make sense? Right? Okay. And what about the second part? Well, the second part, we're just looking at fn minus fm at that single point, and we know that we have convergence at that point, right? So so by 1, we can choose an n past which we have control over this first part, right? And then by 2, sorry to do some bad board work. By 2, right? There exists another n prime, say, past which fn x naught minus fm x naught is smaller than epsilon over 2, right? So this guy can be made smaller than epsilon over 2, and we get our epsilon. Yeah, sure.
I'm still confused on it. When we rewrote the fn of x minus fm of x into that whole thing, how did we get it into those 3 parts?
Well, so the idea is basically that we want to bring in this thing here, right? We want to bring in this term.
Oh, so we just added 1.
We added it and we
0.
subtracted it.
Okay.
We added the term and we subtracted the term,
Got it.
right? So we did nothing basically. It was a cleverly chosen 0, chosen so that we can take advantage of the convergence at that one point, right? And luckily, or maybe not luckily, when we did that, you see that this thing can be controlled by uniform convergence of the derivative. Yeah, I mean that's probably how this theorem was discovered, right? You know, you probably the person who made this theorem was doing things like this. They said, well, if we're trying to get convergence here, suppose we have convergence at one point, right? If we have convergence at one point, then we can actually break this thing into these two pieces. And oh, look, if I have uniform convergence of the derivative, that would give me control over this thing. So convergence at that one point plus uniform convergence of the derivative would give me the result that I want. So that's at least the first part. So right now we've shown that the f sub n's converge uniformly. Okay, let's get to the. Is this okay? Yeah. Okay, great. Okay, let's get to the second part. Okay, so we want to show that. Now we want to show that. So part 2. We want to show that. F prime x equals the limit as n goes to infinity of Fn prime x. Okay. So what we're going to do is let's define a couple of sort of auxiliary functions. So for fixed x, we're going to define these functions. So phi of t is going to be f of t minus f of x over t minus x. Right, so we've already shown that the f sub n's converge to this function f. Let's look at the slope of this function. Okay. So we fix, here's a, here's b. We fix a t, we fix an x, okay, and we say, well, let's define this phi of t to be the slope between these 2 points, okay, between our fixed point x and the variable point t. Okay, and we're going to define phi sub n of t in the same way, f sub n of t minus f sub n of x over t minus x. Okay. Okay. So notice that, of course, phi sub n converges to phi pointwise. Right, because as n goes to infinity, right? As n goes to infinity, we get f here. Okay, and if phi sub n converges to phi uniformly, then we can invoke the theorem that we had before, the theorem that we used to get the continuity. This is why Rudin did it in that full-blown generality, because he wanted to apply it here. So in that case, the limit as t goes to x of phi of t is the limit as n goes to infinity of the limit as t goes to x of phi nt. Right? Do you remember this was the you go along the commutation result, right? Phi of t, right? Phi of t is the limit as n goes to infinity of phi sub n of t, right? Limit as n goes to infinity of phi sub n of t, right? And this was that commutation result. You can take the limit first and then let t go to x, or you can let t go to x and let n go to infinity, right? This was the thing that we used to get the continuity, right? And you see what happens, right? As t goes to x, what is that? Well, as t goes to x, what do you get? Those of you who've been through Calculus 1, as t goes to x, you get, it's too easy, sorry. You get f prime, right? And here, of course, as t goes to x, you get fn prime x, right? So the limit of the fn primes is actually f prime, which is what we want. Okay, so we want to show that these guys converge uniformly. Okay, so that is our new goal. We pull out the big machine that we made earlier, and we see that we just need to prove. So it suffices to show that phi sub n goes to phi uniformly. In other words, that given an epsilon can find an n past which phi sub n x minus phi sub x is smaller. Sorry. Is smaller than epsilon for all t in infinity. Okay. Okay, so let's look at it. Let's consider phi sub n of t minus phi of t. Well, that is, let me make sure that I'm okay here. Oh, actually, let me do it a different way. I'm going to do it as using the Cauchy criterion. Okay, so we're going to find an n past which this difference is smaller than epsilon. So we use the Cauchy criterion, right? This thing is, of course, fn t minus fn x over t minus x. Subtract fm t minus fm x over t minus x. Okay. And so at this point that we'll do what Anne was suggesting earlier. We're going to sort of, we'll put different pieces together here. So let's write this as fnt minus fmt with t minus x minus fnx minus fmx over t minus x. Right, actually, let me combine that together into just one thing. This thing, okay. Okay, so we have this. We have the slope of the secant line, right? We have the slope of the secant line of fn minus fm, right? So we have this function fn minus fm, right? And we have its value at t minus its value at x over t minus x. Okay. We use, at this point, we pull out the mean value theorem. We say, well, that's going to be fn minus fm prime at some point c. Right? But we assumed that the fn primes converge uniformly, right? And that means that we can make this make this thing as small as we desire, right? Since fn converges uniformly, sorry, fn prime converges uniformly, we get that there exists an end past which fn minus fm prime is smaller than epsilon. Right? These guys converge uniformly for all t in AD. Right. So we can, this thing is going to be small over the entire interval, so definitely at that point C, it's going to be small. So using that n, we get this thing is smaller than epsilon. And that's what we want. That's what we wanted. Okay. Okay, makes sense? Makes sense? Any questions? Okay. Okay, so I was going to do, in previous years, at this point, I've shown the sort of gory construction of Weierstrass's continuous nowhere differentiable function. So Rudin, I'm not sure why he puts it in at this point, but just there's this thing called Weierstrass's continuous nowhere differentiable function. I think we're going a little bit slower. I want to make sure that we get to Ascoli Arzela, so I'm going to leave that out. But if you're interested, I can give you the link to where I presented it in previous years. It's basically a kind of fractal construction. But yeah, anyway, so this was kind of a shocking thing when it was created. A function that's continuous, but it's not differentiable at any point. Okay, but if we have time, then I'll come back and do it. But for now, let's just keep on going ahead. Okay. So okay. So from here on in, the question that we're concerned with is the following. So you think, okay, look, we spent the last few days showing that uniform convergence is good, right? Right. It's a good thing to have uniformly convergent, a uniformly convergent sequence of functions. And the question we want to answer now is, when can we get such a sequence? When can we get such a sequence of uniformly convergent functions? Okay, and what you want to think of, the analogy you want to keep in your mind is that of the Bolzano-Weierstrass theorem. right? Where you've got like a compact set. If you have a compact set and you've got an infinite sequence inside of it, then you're guaranteed a convergent subsequence, right? So like K compact, A sub n infinite, then you're guaranteed there exists a convergent subsequence. Okay, and so we want to do something like that. We want to kind of make an analogy for that. Like, what would be a compact set of functions, right? We want something like a set of like a collection of functions that's a compact set, and we'll have some sort of infinite sequence of functions in it, and hopefully we'll be able to get a uniformly convergent subsequence of functions out of that. Okay, and that's basically the idea of Ascoli Arzelot. That's the motivation for Ascoli Arzelot. Okay, because you want that uniformly convergent subsequence because they'll converge to something, and they'll converge to something that preserves the qualities of the functions themselves. Okay, so this is used in partial differential equations. You'll have some solutions for a differential equation, right? And you want to have some sort of limiting solution that still preserves the qualities of the original guys. Okay. I mean, I'm sorry, you don't have a solution. You have these guys who will converge to a solution, but you still want them to be differentiable when you get there, right? And that's why you want uniform convergence, so that the thing that they converge to, the solution that they converge to, actually is differentiable. Yeah. Anne?
What does it mean to be compact when we're dealing with functions? Like, what would a cover of
Yeah.
functions look like?
Yeah, that's a very good question. And so that's what that's what we're spending the next couple of days talking about. Like, what does that even mean? What does that mean? Like we could just say, oh yeah, we've got the soup norm metric, so that's a metric space, and we can talk about compactness in that sense, right? Like, you can have some cover of with respect to the soup norm topology, blah blah blah. That will all still hold, but it's not so useful. And so we're going to do something that we're going to get a theorem that actually is useful. Okay, but that's great. Like, what does that even mean? Okay. Okay. So first thing we're going to do is define a notion of boundedness. Okay. So like a bounded set of functions. Okay. And there are going to be two definitions. So we're going to answer this question in sort of two ways. We're going to get sequences that converge uniformly, and we're also going to get sequences that converge pointwise. Okay, so even though pointwise convergence wasn't that useful, we're gonna try and get theorems that will guarantee us pointwise convergent subsequences. Okay, and we'll use them to get the stronger result of uniform convergence. Okay. So here's how we go. So you have a sequence of functions on a set E. Okay, and the first thing we define is something called pointwise boundedness. If for each point x, the sequence f sub n x is bounded, then we say f sub n is pointwise bounded on E. Okay. Second condition, second definition, if there exists an M such that all of the functions are bounded by m, right, then we say, right, for all x and e, then we say that the f sub n are uniformly bounded. On E. Okay, so pointwise boundedness is kind of a very weak thing. So let me give you an example. So suppose you have a function like this. We call this function f. Okay, and we let f sub n be f minus 1 over n. Okay, then so f1 would be f minus 1, f2 would be f minus a half, etc., etc. Okay. Well, at any point, those values are all bounded, right? Those values are all bounded, and so this is pointwise bounded. Okay. All it means is that at each point, the values are bounded. At each point, the values are bounded. Okay. Uniformly bounded is much. This is not uniformly bounded. Uniformly bounded would mean there's an m, so that all the values of your functions are trapped between m and negative m, right? So at every point in time, your functions are your values are bounded, right? So clearly, uniform boundedness implies pointwise bounded, right? But not the opposite. Okay. So okay. Let me just close with one comment. So here's an example that Rudin gives. So your question is, when do we have a pointwise when do we have a pointwise convergent? So under what conditions can we guarantee a pointwise convergent subsequence? So we're looking for something like compactness, like what kind of thing would force there to exist a pointwise convergent subsequence? And the question Rudin asks is, suppose you have these guys are uniformly bounded, and they're continuous, and they're on a compact set. Right? You've got uniformly bounded functions, and they're continuous, and they're on a compact set. Does that imply there exists a pointwise convergent subsequence? And the answer is no. No, that's not enough. Okay. So I guess I don't have time to give the example, but I'll start with this next time. We're trying to find things that will sort of be in place of compactness. What if you have uniformly bounded functions and they're continuous on a compact set? It's still not enough. Okay. Doesn't guarantee even pointwise convergence subsequence. Okay. So we'll start with this sort of stuff next time.